Yeah, so I'm Wouter Kuijpers. I'm from the Eindhoven University Technology, just like Tech United is. And I'm doing my internship at the university here, more specifically at the Gambara robotic soccer team. So what I want to show you in this presentation are the results and the process I did in my internship. My internship is about 3D ball positioning. I will tell you a bit more in the start. Then we go to some challenges, how we solve them with an actual triangulation algorithm, the results for that triangulation algorithm, and then I will end with some conclusions and recommendations for implementation. So the target is to develop a 3D ball detection system for robots in the MSL League. So several solutions have already been presented, also today. So for example, adding another perspective camera, using Kinect cameras. There are also some things, for example, with the bijection principle applied to the projection of the ball, which makes that actually every projection is unique. And in that sense, you could also estimate the 3D ball position. We're actually interested in a more in another totally different method, I would say, which is focused on cooperative sensing. So my assignment was to research and verify whether this cooperative sensing can actually be used for this purpose. So how does this look like? We work with the triangulation of Omni-Vision camera data. So we have two robots which both make a projection. In this case, robot 1 makes a projection at P1, robot 2 makes a projection at P2, and in the most simplest case, crossing those lines will give you the 3D ball position. This ball position can in the end be used to, for example, give a better estimate of the ball position actually on the field. So in this case, robot 2 will not say that the ball is at this position, but will actually correctly find the position P ball. But also this height of the ball can, for example, be used to design an interception strategy for lob passes. So this has some challenges. I listed here 3 of them. So the first challenge is, for example, that due to noise or inaccuracy, the lines of sight of the robots do actually not cross. Well, this was already solved in a previous research. It's just we're not looking for the actual cross point. We're more looking for the minimum distance between the two lines of sight, and then on the midpoint of that minimum distance line, or maybe another weighted average, you could say that the ball is located at that point. That's already solved, but the more challenging part is actually the communication between robots, because we need to combine Omni-Vision data, and this requires communication. So in this case, we have first one big challenge, which is the communication delay between robots in the robot-robot communication. So as you can see in the second figure, for example, if the pink robot is the actual robot we are, then the data from the peer robot, the red one, will not arrive. It will arrive, for example, after 3 samples. So how are we going to treat that? In a previous research, there was a solution for this, which said we will just extrapolate this projection data up to, in this case, ti plus 5, which is actually like the moment we are currently evaluating. However, in some tests, we found that the communication delay plus some added noise might create a huge inaccuracy. So I came up with another solution for that, which I will present in a moment. Then there is another challenge, which is actually the limited amount of data we get from robots. For example, the robot itself could have some time instance where the ball is not visible because it's, for example, blocked by another robot, or it's just somewhere else on the field. There could also be, in the case of the Gambara team, they do the robot-robot communication at 10 Hertz. So, for example, these could come in like every tenth of a second. How to handle that? I will explain that after I presented this MATLAB simulation environment, which is part of a previous research and some additions I made to see actually the effects those previous presented challenges have on the actual triangulation algorithm. So for that I needed more robots. So in this case you see 3 robots, a green one, a red one, and a black one. They are communicating with each other with a variable communication delay, so it's not constant, it's all over the place, so to say. The robots can actually have a clock offset. So for example, if we timestamp the data, then measurements taken at the same time, same global time I would say, can have a totally different timestamp because of this clock offset between robots. And then there is this package loss, which is challenge 3 on the slide I presented before. So these all are implemented in the simulation, and you can actually see in this visualization that there indeed are some places where there is, for example, one packet lost and there is a lot of noise on the projection. And in this case, the blue line you see is actually the ball as it's detected by the 3 robots you see over here. At this point, the ball was bouncing, it was shot by the green robot, and the green robot is driving behind it, and the red and the black are driving alongside it. Also, I implemented a different ball model just for the sake of being able to simulate both the bouncing dynamics and rolling dynamics. This means that actually the ball model is not only containing continuous states, it didn't actually when it was a bouncing ball, it also had discrete cases, but now it actually has like 2 different parts of the model which are switched between. So then for the triangulation algorithm, so suppose we're now at time tn. To solve the problems, or actually the challenges I stated, the following solutions we came up with is that actually with the communication delay, we want to tackle that in the way that we're actually not evaluating tn, but we're actually evaluating the moment in time when all the data, or some set of data, has arrived from the other robots. So in this case, tn minus 4, that's, for example, a moment where all the data from all the other robots, say there are 3 at the moment, that all the data has arrived. Then we perform the triangulation on that time instant, and we filter it using a Kalman filter. And then actually we're going to, we need actually the ball position at this moment, so we just use the model of the ball to go forward in time. Instead of using, for example, extrapolation to extrapolate the Omni-Vision data to tn, we use a ball model to go forward in time. So it's like a little bit of a switch in there compared to the extrapolation approach. Then as a third, the solution to the third challenge, it's to combine the line of sight we have from the robot with the actual predicted position for that moment of time by the Kalman filter. But I will get back to that in a moment with a bit more detailed explanation about that. Because in a moment I want to continue with an explanation of the algorithm itself. The algorithm consists of 4 main parts. You can also see them right here. It contains a data buffer, it contains a Kalman filter, a triangulation minimum distance algorithm, and it consists this part which we will for the moment call model update. So then to start with, to give you a bit of a feeling how it works, this is the data buffer part. So we start at label number 1. First we update the master clock, and this is actually a graphical representation of the data buffer which is in the algorithm. We see per column the robots, and each row represents a certain time instant. So for example, currently we will be in robot 1 because that robot has the latest data sample. So this loop on the left fills this data buffer and keeps track of how many entries there are in each column and how many entries there are in each row. So after all the robots or the data from all robots has been gathered at a certain time instant, the moment in time we are going to perform triangulation on will be selected. So that moment can, for example, be this moment in time, because we have data from 3 robots at that point. So a triangulation would give great results, hopefully. So this data selection, so this time instant is selected, and the actual the Omni-Vision data is communicated to the rest of the algorithm. And for this, it's important to notice that these measurements can be non-chronological. So it could be that we first triangulate a measurement in the future and then maybe go back because suddenly another measurement arrives from another robot, which actually would greatly improve the accuracy. So in this case, the Kalman filter's prediction state, which is more the left part of this figure, is a little bit different than the normal Kalman filter you would imagine, because in this case it can run the model both forward and backward to like already give a prediction of the ball. So actually you could say at some point we're predicting the past, which sounds quite fun. But this all to provide the prediction to, in the end, update the state with the measurement. So from label number 3, there is the minimum distance, or the measurement actually coming. And this one is applied in the update state of the Kalman filter to the actual 3D ball position. Then also for the next slide, it's important to see that there is also a label 2 here. So this is actually the predicted position by the Kalman filter for that time instant. And this is communicated first to the minimum distance algorithm. So in code you would actually see that we're going, we have this predicted state, then here there is some minimum distance algorithms, and it's going back to label 3, where it's used in the update state of the Kalman filter. So we will now actually move to label number 2, where there are the minimum distance algorithms. So as I told you, there are like 2 kinds of minimum distance algorithms. One is the minimum distance algorithm between 2 lines of sight. So in this case, we would, for example, have a robot at Rx and Ry, and they have a projection at Py and Px. And we determine the minimum distance between the 2 lines of sight, and the midpoint of that minimum distance is actually the 3D detected ball position. This is one, and this was already there. What the Kalman filter added is actually we could have already a prediction for the ball position. So with that line of sight, if we, for example, have only one line of sight, suppose there is a moment in time only one robot sees the ball, to get to a 3D ball position, we actually use the predicted ball position by the Kalman filter, combine that with the line of sight we have. We can determine a minimal distance there, and can also say, well, the actual ball will be somewhere in the middle, for example. Then there is, of course, aside from the Kalman filter, the data buffer, and these minimum distance algorithms, there's also a model update. This is not very interesting. It just iterates the model, the amount of time it needs to get the actual ball position, which is actually in the past, to get that one to the current moment in time. And that's the one communicated to the rest of the system. To actually see if this works, this all, we use this, I did a static test in this case to validate it and to see what kind of performance we can expect from this. So the actual algorithm is implemented on 2 robots, those 2 over there, and I've used 5 different ball positions in X and Y on the field. I will show them in a moment. And 2 different ball heights. So the one is just a normal ball lying on the ground. It's the radius of the ball, 11 centimeters. And also the green box you see over there, that exactly raises the ball up to 42 centimeters. Then for each robot, I took 200 measurements and analyzed those for mean deviation and actually the noise. If, for example, the Kalman filter would maybe not filter too good, or we'll see that in a moment. And it's also interesting to see if there's actually going to be a difference between robots, because in this case both robots communicate, and you would say that they're almost using the same information. But in this case, for example, the data from robot 1 is communicated every 1/10 of a second to robot 2. So there could be times that we actually, because the vision runs at 50 Hertz, there could be executions where we don't have that data from the other robot. Of course, the same happens on the other robots, so the algorithms will provide different results. So now the results. In this case, we see a half of the field, and we see two robots, one over here and one over here, marked by the crosses, for a height of 11 centimeters and a height of 42 centimeters. And at both heights, the dots represent the mean position. The mean position is the position over the averaged over the 200 measurements in that time interval. The mean position and the actual position, which are the black dots. So this is actually the algorithm working on a ball, which is just lying on the field itself. On the right, we see what happens if we actually raise the ball. So then we indeed see that there are very small differences. In this case, the dots are almost completely on each other, so it's actually difficult to show. But what we do see is that in this case, for example, there's quite a huge deviation between the actual position, the black one, and the red and the pink, in this case, position, which are the mean estimated positions of the robot. So in this case, there was actually a deviation of 36 centimeters, but on average, because the other ones are rather okay, we have an average error of 13.4 centimeters. There is not a lot of noise. It actually went down to centimeter level, 0.86 centimeters. So these are those results. So to conclude this part of the presentation, so my assignment was to research and verify whether this cooperative sensing could actually be used in this RoboCup. So a MATLAB simulation environment is used to actually identify the challenges, get a feeling for the topic, and get to some solutions. The new approach is also implemented in the simulation environment and seems to yield quite good results. The triangulation algorithm is also implemented already on the robots themselves. The static test showed that there's a reasonable accuracy of 13.42 centimeters. If I exclude the one which was like very off, so the one which had an error of 36 centimeters, then I end up with a 10.6 error, because I don't trust the measurement which was in the middle. I need to do that one again. And there are still some dynamic tests we actually want to do, because it's also quite interesting to see how this actually will perform in real time. But we didn't have time for that yet, so that will be on the roll, and I guess you will be all posted about that. Some recommendations are made in the total process. Of course, there were some points where we thought this can be better, which have not been implemented yet. For example, at this moment, and you may have also heard it in the presentation itself, the choosing which time instant is actually used in the triangulation algorithm, because this is at the moment variable, that's very easy. We just look at the maximum amount of data in the row. So the time instant with the most triangulation algorithm, triangulation data, Omni-Vision data, will be chosen. But this could, for example, be a much more elaborated algorithm. For example, if you consider the error covariance of the Kalman filter. You want to get that down as much as possible, because then your belief about the current ball state is best. So if we quantify the measurement error, which could, for example, be the robot to ball distance, if the ball is far away from the robot, measurement will probably be more inaccurate. Then the error covariance, I guess this one has to be determined through tuning, or we have to find some other way to determine the accuracy of this model. But combining these allows to actually predict the prediction error covariance, the P. So what I'm trying to say is, suppose we're at the moment the Kalman filter is at Ti, we could try to see if a new measurement comes in with, for example, the ball very close to the robot. That would mean that the R in this case is very low. We have a lot of belief in the measurement. Then it could be worthwhile to iterate the model backwards. Iterating the model will decrease the belief. Then applying that measurement suddenly increased the belief a lot. And then we have to iterate the model, of course, to get back to the same time instant again. What my recommendation is, you can, beforehand, you can actually already calculate whether it's worthwhile to go back, apply the measurement, and go forward again. If the measurement in this case would not be very accurate, it wouldn't make sense to, for example, go back. The current implementation of the algorithm, it sees just that there are 3 robots at this point which provided data, and those are just used because it's the maximum amount of data. But maybe it's not a good thing to do so. Then I have a slight demonstration. It's always, of course, dangerous to do something like that. Let's see. So what I will show is actually with the 2 robots over there. I'm going to move the ball at this point. Yeah, can you attach me? And this is then the base station application of Kambara, which we will put on the screen here. It's actually on that side. And then I will already turn the robot. Actually, does this go up this far? Yeah. Now we need to wait, I guess, for the robots to show up. No, that's it. Our monitors were off. Let me. Yeah, and the other one also. Yeah. So actually now I'm going to introduce a new obstacle in the field, which will be me. And I will do it rather slowly, but in this case you should see that the ball is now lifting off the field. Oh, this is. And actually in this case you also see that there are 2 different balls detected. So, but they are quite close to each other. But if I now move the ball over the field, in this case so I can put it down, roll it, that works fine. And then if I lift it again, it will actually show the 3D position in the base station. So I guess that was it. Oh yeah, of course. Yeah, and then there is one slide telling. Thank you. And if there are any questions.
Of course, if there are any questions.
Is your implementation in C++?
Yeah.
Can you give it to us?
I have to discuss with Kalman for that.
Okay.
Okay, I think this is quite an impressive piece of work for doing in 2 months.
3.
3 months.
Let's
okay.
make it 3.
3 months work. And this is really, really impressive from our point of view. Wouter is always welcome in our lab. Is there any questions from other people? Yeah.
Maybe I already said it, but then maybe I missed it. Have you any idea why the error was more when you have the ball at 40 centimeters instead of on the floor?
Yeah, there are some things which are, for example, the if the ball is in the air, the robot, actually the projection of the robot also increases. The distance from the robot to the actual projection also increases. So probably that will cause that bit more of error. Of course, the one I have to admit, the one in the middle is probably maybe because I positioned the ball incorrectly, that it maybe caused that 36 centimeters I was talking about. But the other ones, I think that they're actually caused by that the distance from the robot to the projection increases, and that it becomes just a little bit more sensitive to, for example, pixel changes or detections of the ball position projection.
I guess that probably there's also some influence from the fact that the blob that you get when the ball is out of the field is different from the blob that you get because of the shadow. Yeah, and the bottom part of the ball is not illuminated, so probably there will be some changes there, I imagine. Yeah.
Could also
this is
be, yeah.
just a guess.
Could also be.
Probably this will also influence that result. Any other questions? Or the invited speaker.
Selfie. It's just a quick question on the timing aspect. So you said that, of course, the delays, they cause inaccuracies, which is, of course, everybody knows. So the question is the other way around. So from the accuracy that you'd like to have, what is the requirement that you think you'd like to have from the timing point of view? So how precise would you like to know the age of your data when it arrives to you or when it becomes available to you?
How precise? In this case, that's actually also yeah. Well, the accuracy of the timestamp in this case should be within 1/2 of a vision sample, because the data buffer, I quantize the measurements or the timestamps actually to the master clock. Maybe I can be a bit more if I have the picture. Yeah. So in this case, the measurements are stored in a grid, which is so they are quantized to the master clock. So in this case, I have the current master clock of the robot, and there is from -1/2 vision period to another vision period. I take everything together, because I cannot perform triangulation or any other minimum distance algorithm if the measurements are like slightly off time. I cannot go work on that time difference. I have to assume they are from the same time. So in this case, the accuracy of the timestamps It would be within one vision period, preferably.
That is pretty large, right? So
Yeah, in this
then you're
case-
saying that you don't really require that much precision, because then you are going to consider them at the same time, and then you're going to use them as if they were simultaneous.
Of course, yeah, so in this case, it's anyway quantized. So if I would get more precision, that would in the end give a better accuracy of the triangulation, that's for sure. But in this case, this algorithm doesn't do anything different. So it's only, for example, this could be used in the decreasing the value of the measurement error covariance, the R I presented. This could be lower if we make sure that, for example, the communication timestamps are really good, or really accurate, sorry.
More serious. Oh my God. Just one point. Currently, we are not synchronizing the clocks between the robots, which is something that we want to do. Okay, but currently we are not.
How can you deal with false positives? So let's say one robot detects a false positive ball, I don't know, somewhere outside the field. Or
Yeah, at this point, that's actually, in this case, out of my scope, out of my assignment. I get the ball position, or the ball projection actually, from the vision system. And I assume that they have taken care of false positives in this case. So, really easy. So, no, so in this case, we don't have anything in this area currently. So we need something, because we have moved from C#.
Okay. All right.
Maybe to elaborate.
No, but that's of course an important question, and a serious question, of course, how to deal with that particular situations.
Maybe a little bit more elaboration on this. So, what was it again? So actually, the ball position it has already the vision module detects a ball, and this one is when it goes through the integrator here in the Gambada robot, and that one already determines whether there, for example, there is a false positive, and filters out those, and then I am left with only one ball position, X, Y. And that's where actually this algorithm comes in and starts working.
Basically, it comes down to the resilience of the work that is before his work,
Yeah.
right?
Which is
Depending on the capacity of taking out false positives.
Yeah.
maybe you could do something to at least see something is strange.
Strange, right?
The closest
Yeah.
distance between those trajectories is
Yeah.
too far away from each other.
Something that we'll probably discuss tomorrow, that you have proposed maybe 1 or 2 years ago, that was to discuss level of confidence of what we get from our vision systems, for instance. I guess. Let's see. Other questions?
Okay, I'll be fast because I think we are a little bit delayed. So I have to reuse the words from my colleague Bernardo. I think you did a very nice job for the small amount of time. So congratulations for that. I think we have here interesting results that, of course, we will share to everyone, not only the present, but everyone on middle size. The question is to maintain a half past really fast. You have interesting results. Of course, it's missing the final part of trying this with the robots and the ball moving. The question is, did you start from the same position in the beginning? At this point, if you have to recalculate your tasks, do you start from where you started before? There was anything that you would like to change
Is there anything
regarding
you would
your
like to
approach?
change? In like the more like on the process side of, or the more the design of the algorithm?
I was thinking more in design of the algorithm. After what you saw, do you think there was anything different that you would like to try in the beginning?
No, actually there is not. Maybe indeed at the clock synchronization, that was something we were scared about at first. Maybe we could have picked that up at the earlier stage to like already implement that to increase accuracy, because at this moment indeed the clocks are not synchronized, or we don't know actually. So, but actually the rest of the algorithm, I think it would end up the same. Yeah.
Thank you very much once again, and congratulations.
Yeah, thank you.
you again, Wouter.